Alright, I'd first like to say that I'm going to try to keep this brief. Mainly, I'm just doing this video presentation as a means of demonstrating what kind of activities I would use and how I would use them, as well as demonstrating a use of technology that could be useful in classroom, or in my classroom. This allows me to present information or show demonstrations on a media format that's easily digestible, and you can upload this to YouTube easily. But I'm going to try to keep this down below 5 minutes, so I'm just going to kind of go through a brief overview of what this demonstration would include to try to keep the file size down. So first off, I'd start by saying that we have several different activities available to me. The first of these activities is exploring the light from gases, which was a step to the discovery that matter behaves as waves as well. That's how we discovered that different properties of light. And it's a good review activity for students to kind of take a look at when they're getting into this subject. It's also just a good overall activity. Like, this is a very good program that you introduced me to that has pretty or already set activities that can be used for some of these concepts that you cover in an actual physics class. So this, and along with the understanding spectra emitted by gas lamps, are two activities that I would definitely like to use in my actual class, not just as added material. But then we get into light waves, and the actual one that we wanted to cover was about matter waves. Now, the first three are just a refresher on about how light waves work, or about how waves work in general. So I'd pull up this little PhET demonstration from Colorado website. You might be already aware with this, but it kind of demonstrates how water works. And if you notice, just with a water wave passing through a double slit, you get a diffraction period. You get diffraction, so you see how it basically zeroes out here, showing you interference. So the waves passing through both of these the one wave passing through both of these slits creates double waves, which meet for constructive and destructive interference. And here you see a period or an area of relative calm. So destructive interference is occurring here, and then you can see constructive interference occurring over here where the wave gets larger. And if you do this again with sound, you will notice almost exactly the same exact thing. And this meter right here is measuring the pressure waves. And you can see how at certain points the waves kind of stop or nullified, and then at other points they get larger. The light wave one is the one that kind of shows it the best, and that's because it presents the screen back here, and you'll notice that it actually allows you to visualize it. So you see where the waves add together, it shows up on the back here. And if you change the color, it makes it a little easier to see. But you'll notice that certain portions change color and become red as the waves add together, and then certain portions are left black. Now that's the PhET demonstration. Now on to the actual activity that I would be using, and this is the activity presented right here. It's a pretty easy to understand format. Most of it's very conceptual. There's not much of this I would change on its own, except for maybe the last portion. I kind of like this first half right here. It does the trick for what I would be looking for in a high school class, just the basic concepts. But if you're looking at the demonstration, you can start with photons, which we know behave like waves, the electromagnetic spectrum, and when you run the simulation, wait, one second, let's separate our slits a little bit. There we go. Now we're actually being able to see the wave. Sorry, the slit resolution was off. Wasn't exactly showing the deconstructive interference there. It's just showing a giant white. But this is showing you kind of the same thing that this did. Almost exactly the same thing. You've got destructive interference happening here, constructive interference. The most important thing is that the photons are scattering outside of just these two slits. So it's not just following the slits and hitting the back. It's spreading out once you get to the back. Then you can do this again with electrons, which obviously have much more mass. And you can see a clear wave pattern here. And that was important because when they did the experiment with electrons, they didn't believe that they would see this because electrons have mass. They are particles. Passing them through the slits, you would expect just to see the electrons hit on the other side of the slits instead of spreading out like this. And in fact, this simulation allows you to do it with protons, which have hundreds of times more mass than electrons, and neutrons. And you see that matter does in fact have wave-like properties. Now, one interesting thing to note here is the slit separation, and this is one of the reasons why it was so hard to discover, because look at the size of the slits for the photons. These are ridiculously tiny. We're talking 10,000 nanometers. So these are very small slits, and it explains, or basically it goes like this. The reason you don't notice this kind of properties in everyday life is because you have to funnel it through slits that are insanely tiny, and we just don't have that apparatus, or we don't encounter that very often in day-to-day life. The importance of this, though, is that it shows that matter behaves like waves, and this PhET demonstration kind of shows that as well. It's just another way of doing it. But it kind of shows here a visualization of what's going on. So you fire the photon, and it becomes a wave. And then when it hits the back, it collapses and it takes on a point. And you can do this with electrons, and you'll notice that they exhibit similar patterns. And you can do this with neutrons and so forth. The end result is all of these different kinds of particles behave in a wave-like matter, and what that wave actually represents is it's not as if the particle becomes a wave when you fire it. The wave is just a probability wave. So the peaks represent the highest likelihood areas, or the highest areas of probability where the particle is, and the valleys, or the troughs, represent where the particle is unlikely to be or where it is impossible to be. This is a probability. It's all based in probability. You don't know where it is until you measure it, until it hits the back screen. That doesn't mean that it doesn't exist. It just means, or it becomes a wave. It just means that we use the wave to represent the probability of where it's going to land, like where it's most likely to be. It may have been a bit shaky. I had to do this all in one go. I didn't quite get the time I was looking for. This is 10 minutes. Running on 11 minutes now, so I'm going to stop it just to save file time, and we'll discuss it.